Morning, everyone. Welcome to one more seminar speaker for our spring semester, Dr. Quing Zhu. I hope I said it right. Dr. Zhu is a professor in the Department of Biomedical Engineering at Washington University in St. Louis, where she started there since July 2016. And before that, she was actually for a long time a professor in the electrical and computer engineering, as well as biomedical engineering at University of Connecticut. So Dr. Zhu's research expertise is in optical techniques and also ultrasound-based techniques, and you'll hear more about the photoacoustic imaging principles as well. With her expertise in these areas, she's a fellow of the Optical Society of America. She's a fellow of the SPIE, which is an International Society for Optics and Photonics. She's a member of the Connecticut Academy of Sciences. And Dr. Zhu has received the Connecticut Technology Council 2007 Women of Innovation Award. She's served also as a topical editor of various journals like the Optics Letters. She's been an associate editor of the Transactions or Biomedical Engineering, an editorial board member of PHOTOACOUSTIC Journal, and also Journal of Biomedical Optics. She's actively taken part in various organization committees for the SPIE Photonics West, the Photon Plus Ultrasound Conference, and also the Optical Tomography and Spectroscopy of Tissue Conference. With that, I'd like to thank Dr. Zhu for accepting our invitation. I wish you could be here in person, but I believe that since you actively come to the OSA conferences that occurs in Miami every other year, I'd hope to invite you in person again when you're around to visit our department and our laboratories and the faculty. So today, Dr. Zhu is going to talk about her research related to co-registered photoacoustic and ultrasound image of ovarian and rectal cancers. I'll turn it to Dr. Zhu.
Thank you, Professor Gavaradi, for introducing me and also inviting me. And good morning, everyone. It's just unfortunate I cannot be there in person. And okay, so today I will talk about our work on photoacoustic and ultrasound imaging of ovarian and rectal cancers. And the first one I will talk is a co-registered photoacoustic and ultrasound imaging for ovarian cancer diagnosis. So I'll give you a little background on the ovarian cancer. And most of you know that ovarian cancer is deadly and no way to screen earlier to diagnose early stage cancers. You can see that most of the survival is happening at the early stage, stage 1 and stage 2. And then beyond stage 2, you see that the diagnosed percentage may be going up, and then survival is very low. So this is a deadly problem. And then before I get into our work into the technology, I just want to show you some examples of normal ovary. This is a very the physiological functioning and normal, very shiny, full of collagen. And then in the later stage of ovarian cancer, you can see that there's cancers on the ovarian surface and kind of messy here. But in the early stage of ovarian cancer, you can see that this is a kind of in between the normal and definitely much different than the late stage cancer. And most often, even surgeons open the abdomen and then look at the ovary, they will not be able to tell whether this is a cancer or not. So it's depending on the HE, which take the tissue out and fixing and then do the diagnosis. But then this is a bigger problem. How do we detect early stage ovarian cancer? And so we can save lives here. And then I also show you a benign ovarian mass. So this benign ovarian mass look a little shinier than this late-stage ovarian cancer, but inside the body it's very difficult to tell whether it's a benign mass or late-stage ovarian cancer because their imaging characteristics are very similar. So I was getting into this research due to Professor Molly Brewer at UConn Health Center at that time. So she gave a seminar on the ovarian cancer, and I learned all the facts. And then at that time, I was working on the photoacoustic imaging. So I said, maybe I can do something for the ovarian cancer. So this is a kind of like a current limitations in terms of imaging for screening of early stage ovarian cancer. Ultrasound is a very low predictive value, and it's recommended not to use ultrasound for screening because you can find out a lot of the masses which are normal and benign, and then end up with a lot of surgeries. And it's not recommended. And there's blood markers called the CA125, but this one specificity is very low because a lot of other inflammatory diseases, GYN problems, diseases can also cause a higher blood marker. And CT scan, you know that ovarian the lesions typically in the centimeter or a couple of centimeter range, that's already considered large, and it could be in the 1 or 2 centimeter range. So this is a small lesion inside the body with a CT scan. The sensitivity is very poor in terms of detection. And MRI is also low sensitivity, also costly. And PET imaging is even lower resolution and compared with MRI and the CT, and is not a good tool for detecting the early stage ovarian cancers, and also distinguishing between benign and malignant masses. So what is the current standard of care? So current standard of care is removal, surgical removal of one or both ovaries if there is a risk involved for patient. So this is considered a gold standard for the current standard of care. And this is the surgical removal of ovarian lesions can reduce the risk of ovarian cancer up to 50%. However, can cause a lot of problems. For example, early menopause, so patient quality of life will suffer, and also the increased risk of cardiovascular disease and also other diseases. So we really need a better tool for detection of early stage ovarian cancer and also for accurate diagnosis of malignant versus benign lesions. So with that, and I was at that time, little over 10 years ago, I was working on photoacoustic imaging for small animals. So before I introduce the ovarian study, and I want to give you a little background on photoacoustic imaging. So what is photoacoustic imaging? And the field is rapidly growing in the past 2 decades. So photoacoustic imaging uses short pulse laser to illuminate tissue. So the absorption of the tissue will produce a small temperature change. So this small temperature change will produce the emission of ultrasound. And ultrasound certainly can be detected by using ultrasound transducer, and then received ultrasound signals can be used as a standard way of the ultrasound detection and the imaging formation, and then form the images for absorber. So absorber typically represent like blood vessels and anything where inflammatory changes can also produce the photoacoustic signal due to the absorption of the tissue. And I mentioned that back a little over 10 years ago, I was working on small animal with Professor Li Hong Wang, and we see a nice vasculature of mouse brain, and this is a before, no open skull and non-invasive, and this is after the skull. The mouse is finished, and then we took out the skull, removed the skull, and then we see a nice correlation of the vasculature with the mouse brain. And with this connection from the mouse to ovarian cancer, and the whole principle behind this is the tumor angiogenesis. And for tumor angiogenesis, most of you know that tumor grow and need nutrients and need blood supply. So there are tons of blood vessels. So this is basically acoustical absorbers in the cancer region. So this is also the principle for imaging cancer using photoacoustic imaging. And with this, and we have two hypotheses. So one hypothesis, we believe that using photoacoustic imaging, we can tag the contrast of tumor angiogenesis. So this is a blood contrast. And second, we can also use the calculate the blood oxygen saturation by using multiple wavelengths. And multiple wavelengths will provide the hemoglobin contrast, which is directly related to tumor angiogenesis, and also blood oxygen saturation, which is related to the tumor metabolism. So with these two parameters, the functional parameters, we might be able to distinguish between the cancers from benign processes. So this is one hypothesis. Another hypothesis is that we might be able to use the photoacoustic imaging to do early cancer detection because photoacoustic imaging is quite sensitive. So we started with the transvaginal approach. And in the transvaginal approach, we use the ultrasound and co-registered with photoacoustic imaging. And photoacoustic imaging, as you already learned, that one way is light illumination, and the other way is the ultrasound reception. So same ultrasound transducer can be used for ultrasound imaging. So we form the B-scan ultrasound imaging, same as the standard of care, the ultrasound imaging. And then we have a fiber connected to the ultrasound transducer and illuminate the tissue. And then we can use the same transducer to receive the photoacoustic wave. And from photoacoustic wave, we can compute hemoglobin concentration and also oxygen saturation. So this is the first example of our patient study. We certainly did a lot of homework on phantoms and simulations and validation. And after like 2-3 years for the study, we fine-tuned our algorithm and also optimized our system. And the first patient study is very encouraging. And this patient is the accidentally, they just find the cancer. And the ovarian lesion is just big. They decide to take it out. And then you can see that in this area, there's a red spot. The red in the following presentations will represent the photoacoustic imaging contrast of hemoglobin concentration. So we see this red spot, there's a signal here. And then later when this lesion was surgically removed, and then we find that there's a T1 tumor. T1 tumor is stage 1, still earlier, and hasn't metastasized and is very localized to ovary itself. And from an earlier chart, you can see that the survival of patients is very high. So this is very encouraging news. And later, we developed, optimized our system. So this is our laser system. And this is the commercial ultrasound transducer and modified with the photoacoustic imaging capability to synchronize with the laser triggering. And now the system is used in the radiology department of Washington University Medical School. And we actually moved the system to the clinical setting around about 20, soon I got here, 2016. And we got a small group of patients. I will show you some results. And we have graduate students work hard on the system. So zoom into our system, what do we have? We have optical setup to couple the light through the 4 optical fibers. And then the optical fiber will illuminate the tissue and synchronize with the reception of photoacoustic imaging. We also have ultrasound imaging co-registered and is real time. And the ultrasound transducer is a typical transvaginal ultrasound transducer we can get from the market. And the laser is iliac laser pumped with 10 nanosecond, 15 hertz. And the wavelength is tunable. So we can use 4 or 3 optical wavelengths to robustly compute the hemoglobin concentration and also oxygen saturation. And this is the very first image patients we got when I moved to Washington University in St. Louis. And this patient, you see the CT here, this is a CT. And then there was some solid component in the cystic area, but they don't know what it is based on the CT imaging appearance. And then ultrasound, you can see that there's a big cystic lesion, which corresponds to the cystic lesion here and there. And then there's some darker area, low echogenicity, and then correspond to some acoustic attenuation. But then when we turn on the photoacoustic imaging and co-register with ultrasound, we see a higher total hemoglobin concentration in this region, and you see color. And then we also can compute, we zoom in to compute the blood oxygen saturation, and we see a low oxygen saturation. So this is a kind of the typical cancers with higher blood content and lower oxygen saturation. And I was going to show you a couple more examples. So this patient is very interesting. This patient has 2 sides, right? One side is turned out to be a cancer, and then the left side turned out to be normal. This is a very rare case. And then we also, the red corresponds to hemoglobin concentration. You see very high in the red ovary, right ovary with red color here. And the SO2 is lower. And in the normal, the ovary and the hemoglobin is lower, oxygen saturation on average is higher. So this is very encouraging. And then I show you some statistics for our first small group of patients of 20 patients of 26 ovary, which is in radiology. And the hemoglobin, this is a hemoglobin concentration. You see this cancer group is higher than the benign, the normal group. And then we also have 3 other type of low grade or borderline grade, they call borderline tumors in the ovarian lesion category. So those 3 were lower risk, but we couldn't distinguish based on the hemoglobin contrast for these 3 low grade or borderline cases. And then we look into the oxygen saturation, and we find that these 3 low-grade and borderline cases are grouped well with the invasive ovarian cancers, and then all lower than the benign and the normal ovaries. So this is result is very encouraging. It says we have 2 functional parameters, and then one functional parameter is hemoglobin, which is a very good separation between the benign, normal, and the low-grade tumors, and then shows almost twice of higher contrast compared with the benign normal lesions. And then we also had blood oxygen saturation, which actually can separate the low-grade and borderline tumors from benign and the normal lesions. And with this encouraging information. So we also further did the analysis using multiple parameters, and the parameters include the hemoglobin concentration, blood oxygen saturation. We also did the histogram analysis to extrapolate the parameters like mean values, coolness and kurtosis, and energy. We also did the Fourier transform. So Fourier transform here correspond, we call this a spectrum analysis. So Fourier transform is the A lines, is the A line scans in the tumor area. And then we average them to transform each of them to Fourier domain, and then average them to plot the slope. So this slope is also a significant parameter to separate the malignant from benign. And this case is a benign case. You see a higher oxygen saturation, lower hemoglobin concentration, and the histogram is different. It's more toward the higher end for SO2. And then for SO2 in the cancer case is more skewed to the lower end, and spectrum is also different. For spectrum, the cancer case, it turned out to be a little smaller slope because of the rise of the tumor angiogenesis. And then for benign, so the slope is larger. And we did the analysis in terms of feature important, and then we also had radiology to read the lesions for the first small group. This group had 40 patients for all the ovaries. And the radiology rhythm, we see the radiology rhythm reasonably well, but it's not perfect. ROC is only like 0.8 something. And the hemoglobin is an important parameter. And also the spectrum slope, SO2 saturation mean value, energy and school, and also the spectrum intercept slope and the intercept of different wavelengths. And those are the p-values. We find that this feature important is more important than just the statistical p-values. But p-values give us indication that whether the two groups, cancer versus benign, can be separated or not. And then feature important tells us that if we want to do feature analysis, which are the features which are very important for diagnosis. And with this, we developed this called a support vector machine classifiers. And we evaluated the parameters in terms of the significance of generating the ROC curve. So the top one is the training and validation. So we rotate, you can think, shuffle the data set into 2/3 for training validation and 1/3 for testing. And we find that the SO2 mean value and also hemoglobin mean value and the radiology ranking, and all together will give us testing data, which is more important for compared with training. Training, you just train the classifiers, and testing tells you the performance of the classifiers. So we find that SO2 mean value and spectrum intercept is in addition to slope, there's an intercept with the y-axis, and the mean value and radiology ranking will give us the values in the ROC around the 0.92 and 0.93 range. So this is our first group of pilot studies. And then with our initial success, we received the second round of NCI funding, and this funding started last year, January. Unfortunately, we hit the pandemic. We were shutting down for a couple of months, and then we were backing on the August, and we recruited so far 28 patients. And this one shows the new study, second round, and this is like a screenshot. We significantly improved our software, and we can actually almost real time to provide the ultrasound as a background, and then again, color is the photoacoustic imaging, hemoglobin concentration, and then the we also can just select the region of interest and then compute the oxygen, blood oxygen saturation. And this is correspond to the image here with blood oxygen saturation. And this case is very interesting. So this case, if you see the ultrasound background here, it's ultrasound. And this case had like enlarged the fallopian tube. So fallopian tube is believed to be the origin of the invasive ovarian cancer. This is called the high-grade serous carcinoma. Is the most lethal type of ovarian cancer. And then the fallopian tube believed is the origin of this. But no one really demonstrated that you can image a fallopian tube because it's smaller in terms of size. And in this particular case, the fallopian tube is more enlarged, and we can see ultrasonically. And the ovary is here. But then we see interesting that we see the hemoglobin contrast and oxygen saturation in this case is moderate. And this one turned out to be a high-grade serous carcinoma of a fallopian tube, and the ovary here is normal. So this is very encouraging. It indicates that in the cases that we can kind of see the fallopian tube when there's visible in the ultrasound, the resolution range, and we have a good chance for detecting the early stage ovarian cancer. Not only that, we also see the cancers in the fallopian tube. So this is very encouraging. And then this example, I want to show you that this is ultrasound. You can see it's a big mass. And then the photoacoustic imaging showed basically no signal. We have some skin signal here, and I present in all the cases. And this inside the lesion, big mass, there's nothing there. And radiologists give it a very high suspicious reading for potential cancer. And then we basically see nothing for using the photoacoustic imaging. And this one turned out to be a large benign fibroma. It's a kind of a big benign fibrostic lesion and quite large. And this give also the promising result. And remember, we also had another hypothesis that ovarian cancers versus benign lesions could be distinguished with the blood signal, which is obtained by photoacoustic imaging. So with this first 28 patients, this is up to February this year. And then we ask our radiologists to read the cancers. This is before the surgical removal and final diagnosis. So they have some kind of a suspicious reading. And this is all the cancers. And we have five categories, and they call it ORAS. It's similar as like a BI-RAS, breast BI-RAS. It's just grade the cancer potential chance of cancer. So let me explain a little bit about this ORAS. So for malignant cases, they give a very highly suspicious malignant cases. This is diagnosis. They don't know the final result. And they give it ORAS 5 is more than 50% chance of malignancy. And ORAS 4 corresponds to 10 to 50% chance of malignancy. ORAS 3 is a less than 1% chance of more than 1 and less than 10% chance of malignancy. ORAS 2 is less than 1% malignancy, and the normal ORAS 1 basically is normal. And you see they're really, they read reasonably well to have all the cancers in this ORAS 3, 4, and 5 range. So they're doing reasonably well here. But if you look over here, this is a category of the solid benign lesions. And then they spread out, and some spread into highly suspicious in terms of malignancy, like the previous example I showed. And this is an area we see a photoacoustic imaging can significantly improve the performance. And then another category is a cystic lesion. Ovarian cyst is very, very common. And some cysts have a solid component, and also very likely their chances of being malignant because of the solid component. And then you see this is the scores are kind of spread here. And in the another small category, this is related to some inflammatory changes, and another category is normal ovaries. And this is a group of higher risk patients, and most of them are having a normal ovaries, and high risk means that they have some genetic mutation, and they get monitored for a couple of years until they're done with their children, children, and then they will decide they want to get their ovaries removed. So this is a group of patients I also show you, but we don't have the gold standard yet because they're still carrying the ovaries, and then we're monitoring them over a 2-year period. We want to see how well the photoacoustic imaging can do in terms of predicting the cancer versus normal process. And so this is 3 experienced radiologists, and particularly Dr. Carrie Siegel and Dr. Middleton. They have 20 total together. They have added together 50 years of experience. And you can see that this area and also this area, they spread out because of the difficulties of distinguishing between benign and malignant processes. And for this new group, this is our bar plot. This is relative total hemoglobin. And you see that cancers stood up. And then this is a solid mass I just showed. And this is the cystic lesion. And this is a small group with some inflammatory changes. This is a normal ovary. And this is a high risk group of patients who are monitoring. And hemoglobin contrast can separate reasonably well from cancer with this 4 type of benign lesion and the normal ovaries. And it doesn't really quite do well with the high risk group of patients because the high risk group of patients, they're young, the ovaries are very active, they are all premenopausal. But if you look over the oxygen saturation parameter, you can see that the cancer is low, as I explained before, and the other benign lesions are higher. And also this high risk group of patients, the oxygen saturation is also higher than cancer. So this is a promising parameter for the high risk group of patients versus cancer. And then we did the ROC analysis. So we did the ROC analysis for radiologists because for 3 radiologists, recently have another radiologist joined us. We have 4 radiologists, and they read the lesions based on the ORAS, like I explained, and they're doing reasonably well with the ROC. Are under the area under ROC with 2 rounds of reading, and 1 radiologist read the different cases. And then we grouped all the 2 rounds together. The ROC can be around 0.92, 0.93. And then we combine the hemoglobin and also the oxygen saturation. We are also getting in the same range, ROC of 0.93. And the important thing is that when we do a logistic regression, to combine all the radiology reading with our hemoglobin and also SO2 parameter, we see that they're complementary. As you can see before, that there's a big solid mass. Basically, photoacoustic doesn't give any signals, but radiology have a trouble to read them. And now if we combine all the parameters, we can achieve quite a good performance with ROC show here, and the area and the ROC is perfect. Certainly, this is a small group of a patient, and right now we're recruiting more. With this 4 more years, we are actually targeting about 200 patients, and also the follow-up with 50 patients of high-risk ovarian, the potential ovarian cancers, high-risk group of patients. So in terms of quick summary, our initial data showed that 2 functional parameters, also including the spectral information, can be quite useful for better identification benign ovarian, the ovarian and adrenal solid masses from cancers. And then also photoacoustic imaging correlated with ultrasound can be quite good for some cystic lesions with solid component and separate this type of lesions from cancers. And then the role for correlated photoacoustic ultrasound imaging on high-risk patients would be the oxygen saturation parameter. So right now, we're still following up with this group of patients. So I'm really grateful for a great team at Washington University. We have a radiologist led by Dr. Carrie Siegel. We also have GI and surgeons. They're all excited referring patients and led by Dr. Mashu Po. And we also have a pathologist, Dr. Ian Hageman, who helped us with the data analysis from pathology perspective. And now I switch gear to the rectal cancer. And for rectal cancer, as 1/3 of the colorectal cancer is rectal cancer. So in terms of statistics, so rectal cancer incident in 2020 around the world is about more than 700K, and with about 300K deaths. And this is a kind of very complex issue. So what is the current management scheme? So currently, if a patient is diagnosed with rectal cancer, and they will get a radiation and chemotherapy. And certainly this group of patients receive radiation chemotherapy, their cancers are still reasonably local. And then the chemotherapy and radiation, basically the goal is to shrink the tumor. And in the back to like several years ago, all the rectal lesion, the rectal cancer patient after treatment, they will cut the rectal out and prevent further potential recurrence. But then with recent years, there's called a wait and watch approach, because this is a big issue for patients. This is, if you cut a patient rectal out, basically the patient quality of life is significantly affected, and they have to permanently depend on the tube. And the wait and watch approach basically say that, okay, if we have no evidence that there's still residual tumor after treatment, we just follow you up very intensively, 3 months for the first 2 years and 6 months for the coming years. And then if at any time point, and there's a potential that the cancer recurred back to the original, the primary site, which is rectum, and the patient will go back and then get surgery. So this is, again, very complex issue. But the trouble is that there is no good imaging modality to identify the residual tumor versus complete responder. Complete responder means the no tumors left. So there's the 20% of this type of patients who already have a complete response with no residual tumor, but because of the lack of imaging tool, and then surgeons will not know for sure there's a cancer or not. So they have this conservative approach to cut the patient rectal out. So this is a really big problem for patient quality of life. And so we were introduced by this problem by Dr. Much, is the division chief of colorectal surgery. And then he had a resident, Dr. Will Kampman, who was helping us on the clinical studies. So we were like thinking, okay, so how can we use the photoacoustic imaging? Or may not be photoacoustic imaging, but other modalities. We have, for example, optical coherent tomography. We also have a diffuse light. So can we use optical imaging to do locally to detect the residual tumor versus non-complete response? And certainly the sensitivity will be better than MRI, because MRI right now is used. And so also the surface examination used, so the visible light is used, but we can go deeper. So for photoacoustic imaging, you already learned the principle at the very beginning. And then photoacoustic imaging also has a couple of variations. For example, this one is called optical resolution photoacoustic microscopy. An optical photoacoustic microscopy uses laser to illuminate the tissue. And then the illumination is similarly generating a photoacoustic signal. And because the ultrasound transducer is focused, so received signal is higher in the focal range. And then if we scan through this transducer, we can get a B-scan image. So let me replay this one more time. So we use laser illuminate the tissue broadly. And then we use ultrasound transducer, focus ultrasound transducer to receive the signal from focal region of the target of the absorbers. And then we scan the single transducer with a high resolution, a high frequency, so we get a high resolution, and then we can form B scans. So this is called acoustic resolution photoacoustic microscopy. So we developed, initially we developed this probe, and it can be like a probe with a side firing, and also can be probe with forward firing in terms of laser. And the ultrasound is detected by using this ring transducer. In the center of the ring, we have a hole to let the light coming out. So this is the whole setup. And I'll spend some time to explain quickly about what this the data we observed from patient ex vivo sample study. We started from ex vivo because we don't have no idea on the photoacoustic signature of the cancer versus the treatment responder. So in this case, on this row, the column here, and this is normal. You can see this is an ultrasound, and this is the specimen and scan direction. And we see that for normal rectum, we see this nice, the pattern for the vasculature. And this corresponds to a normal rectum tissue with these veins and small arteries in the mucosa and submucosal layer. So this is fit nicely to the physiology description of the rectal tissue. And this is a cancer. You see it's quite messy and tons of tumor angiogenesis, the vessels due to the tumor angiogenesis, and quite distorted. And this one is a complete responder. If you look down this column here, and this patient had a complete response. And you see that normal kind of a normal recovery of the normal ultrasound layered structure. And photoacoustically, we see that this pattern is getting back to a normal layer-like distribution of the vasculature. And this patient had a complete response, no residual tumor left. So with those patterns, observed patterns of responders versus cancer and normal rectal tissue, and we kind of very encouraged. So we developed this in vivo probe. We can go into image patients with the acoustic resolution photoacoustic microscopy. And this is our setup in the OR, and we image a patient before their surgery because we need a comparison with the final pathology. And this is what we see with the patient as kind of predicted with the ex vivo finding. And we see that in this case, there's cancers here, residual cancers here. MRI showed that there's still residual tumor in this case. This is a good case for MRI. And then photoacoustically, we see a kind of disruption of the normal vasculature pattern we observed in the ex vivo study. And you see the vessels here basically very irregular, and then compare with normal region here, very regular pattern, vasculature pattern. And this two correspond to the same patient, but in the normal region of the rectum. And this is ultrasound, and this is a photoacoustic imaging. We see this nice layered structure in terms of vessel distribution. We also see this nice layered structure in ultrasound. So this is the kind of a confirmation with our ex vivo finding. And then with all of these patterns observed by our analysis, we were trying to come out with some quantitative analysis, but it was not very easy because those are all qualitative observations. So we decided that what if we develop a neural network and to let neural network to recognize those patterns with normal and complete responders versus cancer. So we developed this neural network model with a very simple two-layer convolution neural network with two convolution layers and two pooling layers. And then the output are very simple, normal versus cancer. And then certainly complete responders fall into this normal category, and the other category is the cancer. And we obtained about the total of 22 patients ex vivo samples and 5 patient in vivo images. And then we used those as our training and validation data set. And then the boxes you see here before, we basically select the region of interest, and then from the cancer, we put into the neural net. We train the neural net to say this is cancer, cancer, cancer. And then for those normal regions, we also have a region of interest we put into the neural net. We teach the neural net this is normal, normal. And also including the complete responders, we teach the neural the same thing. So with this simple approach, and we're quite successful. So we also later recruited 5 more patients, and these 5 more patients were never seen by this same neural network before. This is a kind of very typical that you train the neural net and then input the unseen patient by the neural net to the system to see how's the performance. So in the top one, this 5 patients in the normal region. And you see that ultrasound corresponds to nice layer structure. And here's a hole, this is due to the bubble. And this is a photoacoustic imaging. You see this nice vasculature distribution around the mucosa and submucosa. And this is all the normal region. And in the cancer case, there were all kinds of different patterns that we see. So this is the scope, the visible light endoscope image. Surgeons use this to visually see the surface, examine the surface. And this is an MRI, and this is a diffusion weighted MRI, functional MRI. In this case, MRI sees some residual tumors in this area. And then we use ultrasound to see how's our neural network. And remember, our training is normal versus cancer, and we use 50 as a cutoff threshold. So in this case, ultrasound didn't really detect the residual tumor, but photoacoustic detected the residual tumor with very low 28% output, which is very low, correspond to the cancer. In this case, MRI didn't really see, there's a little residue here, and visibly you cannot see, and then MRI didn't really detect the cancer, and then ultrasound also detected this area with residual tumor, and photoacoustic also detected the residual tumor with very low output. And ultrasound is very close to 50 cutoff threshold. And in this case, MRI is completely missed the lesion. And ultrasound also missed the lesion with high output as normal, but photoacoustic imaging pick up the lesion area. And this case is also the MRI pick up a little bit, and then ultrasound didn't fail to detect, and then photoacoustic imaging detected the abnormal region, which corresponds to the cancer, and with a very low probability of normal. And this case is a complete responder. And you see MRI here show the lesion, and ultrasound basically detected the complete responder, and the photoacoustic imaging show the higher output, which correspond to normal. But this patient still has the rectum cut out because the current standard of care shows the residual tumor. So now I want to show you a quick movie to get some ideas about what is a neural output, network output. And you pay attention to the green box, and the green box in the picture had a tumor bed, and the output is low. And the blue box, the output is higher, that corresponds to the normal region. I'll play again. And this patient had a residual tumor. You see the green box here with a low output, which corresponds to tumor bed. And then blue box here corresponds to a higher output. And there is no tumor in this region. And this patient had a residual tumor. And then another one, this patient had a complete response. And you also pay attention to the green box area. That was a tumor bed, a treated tumor bed based on the ultrasound and the surgeon's inspection. Output is quite high. And the blue box output is also high because this patient had a complete response. I'll play again one more time. And you see the green box area output is high, which basically no tumor left. And then the blue box areas correspond to the healthy region, and output is also high. Okay, so with that, I think I'll just, I want to just show one more curve, which is ROC, and then from the test, this is a testing patient, 5 patients, we we uniformly selected a region of interest for normal and cancer, and we achieved ROC of 0.98 with photoacoustic imaging. And then for ultrasound, the area and the ROC is quite low. So with the summary, and this is a pilot study, our data recently published in Radiology, and the data showed that photoacoustic combined correlated with ultrasound that can detect the recovery of normal submucosal vascular architecture in complete tumor responders with no tumor left. And then in the tumor residual cancer bed, the tumors disrupted the normal submucosal vasculature and displayed some dark areas, no signal, devoid of photoacoustic signal. And deep learning neural network in this particular application seems very valuable to aid us in the diagnosis and automate the data analysis. So currently we're trying to also recruit more patients to the study. And with that, I thank the funding agency to fund this work, and also the Cancer Center, the Washington Universal Cancer Center. And this is like a student I want to thank over the past to help develop the system. And we actually, at some point, back to a couple of years ago, we have our own homemade system, ultrasound homemade system, and then the laser system. And then the first patient actually were obtained, first 2 patients were obtained from this homemade system. And later we purchased a commercial system and then connected synchronized with photoacoustic imaging. Okay, so I'll be happy to answer any questions, and thank you very much to stay with us to listen to our research. Okay, thank you.
Thank you so much, Dr. Zhu. That was an excellent talk. I mean, in an hour, you were able to cover completely 2 different areas of applications of your technology on the ovarian and the rectal cancer, and taken us all the way from how you had the device put together to actually getting clinical validations and developing ORAS. That was very exciting. So
thank you.
There's a lot of questions that you have. I'm going
to
good. First one. So I see some questions are related to your ovarian cancer and some are to the other ones. So the first question is, it's anonymous. I don't know who asked it, but one of the students or faculty, there's a lot of women who struggle with menstrual cramps because of polycystic ovaries, and many a time the doctors prescribe birth control pills. So the question is there a relationship between birth control pills and ovarian cancer?
A good question. And this is really kind of something we try to figure out, particularly from this higher risk group, because they're young, premenopausal, and some are taking birth control pills and some are not. And so we're in the process of trying to figure out is any correlation with development of cancer and the birth control, and also image with photoacoustic signal to see if any correlation. We can't say anything right now, but we have enrolled in the past year, we enrolled 8 this type of patients, and we don't have data yet. Thank you.
Sure. Another person had asked, thank you for your talk, Dr. Zhu. Aside from the hemoglobin and the oxygen saturation, is there a way to use other different wavelengths to extract concentration of other endogenous chromophore concentrations that may distinguish between the benign from malignant lesions?
Good question. So our laser is tunable. We can tune from 600 nanometer all the way to about 100,000 nanometer. But the penetration is still best in the near infrared. So that's why in our ovarian cancer study, we use the full optical wavelengths from 660 nanometer all the way to 830 nanometer. For the colon rectal cancer, because we require faster speed to spin single transducer, so that one is 1026 nanometers, a little higher wavelengths. And the depth of penetration, you can tell that for colon rectal cancer study, we don't need that deep. And we imaging some mucosa, and we can get a couple of millimeter to 1 centimeter. So it really depends on the depth of penetration and particular applications.
Thank you. Is related to your acoustic resolution photoacoustic microscopy, which is done in vivo. Do you see strong motion artifacts, and how do you reduce or eliminate them?
Good question. So motion artifact, it definitely will cause a problem. But in those type of patients, because of the pain involved, before we image, currently we image a patient before the surgery, they're already under anesthesia. And there's no motion basically, and very stable. And late in the next study, we also plan to monitoring patient before the treatment, during the treatment, and also follow them up if surgeons decide to put them on the wait and watch list. So under those conditions, and most often, patient also examined under anesthesia. So if that for the anesthesia, for this cases, the motion is not a big problem. Yeah, there was some bowel movement, but we really didn't observe any significant problem in this case.
Thank you. The next question, switching gears to colon cancer right now. I remember that the most effective way for colon cancer or polyps is by colonoscopy. However, are there medical machines being developed or that are currently exist to also help identify colon cancer or polyps?
And this is correct. This is more related to screening. So the study I showed were more on monitoring the treatment and predicting the treatment response. For the screening, currently colonoscopy is kind of gold standard, right? It's quite accurate, and you just detect, scan through the lung colon region and detect the polyps and also cut them out right away. And this technology is not particularly aimed at that. And the optical coherent tomography, actually, we are also developing, and we recently getting very close to get IRB and then moved into the patient study. But that was for screening. This study I just presented is for predicting treatment response. Yeah.
Thank you. We have from Lin Tong. Thank you so much, Dr. Zhu. Very promising. Could you briefly mention how to perform photoacoustic simulation for ovarian cancer?
And for photo simulation, there is called a K wave in photoacoustic simulation. and you can simulate the performance of photoacoustic imaging. And we actually did not do a lot of simulation. We did mostly on the phantom studies, blood tubing, when we validate our technologies, because we know that simulation is very valuable if you develop something new algorithm. But in our case, we really want to validate our system performance. So we didn't do much in terms of a simulation, but certainly there are simulation tools like K-Wave developed by College of London, and you can use those tools to simulate. Yeah.
Got it. Thank you very much. I see these were all the list of questions. Once again, I would like to thank you so much for giving
Thank you.
a talk and presenting us with multiple technologies.